All right, in this video, we're going to talk about the mole concept, or calculating moles. The idea behind the mole is it's a counting unit. Just like a counting unit is a dozen, or a dozen is a counting unit, that means we have 12 of anything, right? It doesn't matter what it is. You could have eggs, you could have people, you could have planets. It doesn't matter how big or how small. A dozen of something is 12, okay? If you have a ream of papers, it's, I don't know, 500, I guess. Those kinds of numbers are names for different quantities. Well, for us, in chemistry, we're going to count things that are infinitely small, so freaking small, and those are called atoms, molecules, or ions, as you can see on the board here. They're very, very small, so we need to use a number that's very, very large, and that's called Avogadro's number, or 6.02 times 10 to the 23rd. Okay, so just to give you an idea, 6.02 times 10 to the 23rd. Oh boy, I ran out of room there. But anyway, it has 6.02 with 21 zeros after it because you have two places there. So 6.02 times 10 to the 23rd is a tremendously large number because we're counting things that are really, really, really small. Okay? So now, if you notice, I have a conversion factor here. I have a conversion factor. 1 mole of anything is this many particles. So it doesn't matter if I'm talking about infinitely small particles. I could be talking about popcorn kernels. I could be talking about basketballs. I could be talking about planets. It doesn't matter. It's just a counting number. 1 mole of anything is 6.02 times 10 to the 23rd of those pieces. So if I'm going to actually calculate for those, we're going to use dimensional analysis, which is why I taught you that initially. So let's write out here 6.81 times 10 to the 23rd atoms. And you got to write out atoms of gold, dot line. Okay? So if I have atoms here, atoms go down here. What number goes with atoms, molecules, or ions? Well, it turns out, let me erase some of this garbage here. If I take a look at atoms, molecules, or ions, you'll notice that 6.02 times 10 to the 23rd always goes with those. So whenever you have atoms, molecules, or ions, you write 6.02 times 10 to the 23rd with that. So let's write 6.02 times 10 to the 23rd atoms of Au is equal to 1 mole of Au. Okay, for now it's going to be 1 mole. All right, it's always going to be, I shouldn't say that. For now, it's going to be 1 mole. You always write 1 next to moles. Now, if you put this in your calculator correctly, you should get the following answer. And again, I'm just going to coach you up real quick once on this, and you can rewind as much as you want. But on your calculator, you're going to type in 6.81. Then you're going to find the second second button, press it, and then find the button above the number 7, typically on TI calculators. It's called the EE button. Okay, that's the exponent. You'll see a small capital E pop up on your calculator, and then don't do anything else, just type in 23. So your calculator says 6.81, little capital E, 23. Then you want to divide by 6.02, second function, EE button, 23. Press equals, the answer is 1.13. Okay, so we end up with 1.13 moles of Au. Okay, try to get that. Let's jump down here. Okay. So again, now we have how many moles of 4.99 times 10 to the 19th atoms of carbon. So write down what you know. You know you have 4.99 times 10 to the 19th atoms of carbon. Okay? Now, I have atoms here. I better put atoms down here. I'll ask over and over again, what number is associated with atoms, molecules, or ions? And that number is Avogadro's number, which is 6.02 times 10 to the 23rd, and that's equal to 1 mole of carbon. Okay? So again, let's work with our calculator. 4.99, second function, EE, you just press it once. I know I say EE, that's the name of the button. What's that, 19, divided by 6.02, second function, EE, 23. Press equals, you end up with, a very small number, 8.29 times 10 to the minus 5th. Moles of carbon. Okay, 8.29 times 10 to the negative 5th. Okay, it's a very, very small number. So if your calculator says, that's the same number, okay? Just don't panic. All right, let's try one more. So if we take, again, atoms, molecules, or ions. So if I have 1.99 moles, write down what you know, it's 1.99 moles of calcium hydroxide. This is a molecule, or molecularly written. So if this is a molecule, again, I have moles here, moles down here. It's always, well, for now it's 1 mole. okay? How many molecules? Well, that's 6.02 times 10 to the 23rd molecules, because we're looking for molecules. And yes, you have to write out molecules. I don't care if you write it sloppy. You just have to write it. So 1.99 times 6.02 is 1.19 times 10 to the 24th. Okay? 1.19 times 10 to the 24th. So I'm just matching things up just like I did before. Okay? Notice this question says ions. Again, don't be daunted because, again, Avogadro's number, or 1 mole of anything, is 6.02 times 10 to the 23rd. Atoms, molecules, or ions. It doesn't matter. Okay? That's what we'll stick with when we talk about Avogadro's number in those calculations. Okay. We'll do that one in class. Now, help me out here. If molar mass, first of all, molar mass is found on the periodic table. It's the same thing as the mass number. Okay, first of all, just let me say that. So the mass number of carbon is 12.011, but that's the molar mass as well. So that's grams for every mole. Okay, so let me do an argument here. Okay, if we have let me see here. Let me do this. If I have a dozen bowling balls versus a dozen styrofoam balls, okay, which one has more particles? Which one has more pieces? Well, they're the same. It's a dozen and a dozen, okay? You have a dozen of these, you have a dozen of these. No big deal. The question is which one's heavier. Even though the particles are exactly the same, these are heavier, okay? So if I have a dozen little carbon atoms and I have a dozen humongous lead atoms, they have the same number, a dozen, okay? Which one's heavier? The collection of the lead atoms are heavier, okay? Let me go one step further. Instead of a dozen, if I have a mole of carbon atoms and I have a mole of lead atoms, are they the same number of pieces? Yeah, it's a mole, or 6.02 here, 6.02 times 10 to the 23rd here, 6.02 times 10 to the 23rd here. It's the same number of particles, same number of atoms. Which one's heavier? This one. So again, even though the particles are exactly the same count on either example of bowling balls, styrofoam balls, or carbon atoms versus lead atoms, even though the numbers are exactly the same, the collection of those numbers has different masses. So what I'm going to do is look up these masses on the periodic table. So whenever you see mass, and I can't say this enough, whenever you see mass, grams, if grams are asked for or given in the problem, you need a periodic table. So finding the molar mass of these things aren't bad. You just look them up. This is 15.99. We're going to go 16 grams per mole. Sodium is the same thing. It's 22.9. So anytime you see 0.9, round up. Okay? This is 22.9 on the periodic table. We'll say 23.0 grams per mole. Now, I'm not going to do all these, but whenever you have two things together, you just add molar masses. So you're going to add 23 plus 35.5. Whoopsie, 35.5. The molar mass is 58.5 grams per mole. Okay? So anytime you see collections of stuff, you add them together. So notice I have 12 carbons. So I have to add 12 carbons. I have to add that to 22 hydrogens. I have to add that to 11 oxygens. Okay? Real simple step, but just don't forget it. So 1 mole is equal to molar mass. Okay? So what I mean by that is if we solve some problems with this, if I have, write down what you know, if I have 2.91 moles of copper and it asks for the mass, that means I need a periodic table. Well, if I have moles here, I have moles down here. Why is it 1 mole? Because that's what our conversion factor says. Our conversion factor says 1 mole is equal to molar mass. Where do we find molar mass? On the periodic table. So again, I've set my problem up. I know I need grams. What mass is of copper? Well, that's, if you look on the periodic table, it's 63.5. So now I'm going to multiply 2.91 times 63.5. And I end up with 185. Notice I keep sticking with sig figs. By the way, always use 3 sig figs. 185 grams of Cu. I think it was 185, wasn't it? Yep. Okay, now let's go to a tougher one. Now I have this one right here, where I have 0.99 grams of water. So grams is mentioned. Make sure you have a periodic table handy. Grams of water down here. So grams matches with grams to cancel. But now I need a molar mass of H2O. So if I have H2O, if I look up the molar mass of hydrogen, it's 1, but there's 2 of them, so it's 1 plus 1. Again, I'm using the whole numbers here. It's a little easier. Plus an oxygen, which is 16. So 1 plus 1 plus 16 is 18 grams per mole. So let's go 18 grams per mole. So notice I just added that up. 0.99 divided by 18 is 0.055 moles of H2O. Okay? Moles of H2O. Let's try some tougher ones. Okay, these two are some of the tougher ones you can do. Okay, so we'll do the top one and I'll do the bottom one in class. So if I have 4.31 times 10 to the 22 molecules of O2, molecules here, so molecules has to go on the bottom. What's it asking for? It's asking for mass. Mass goes on top. Okay? What number goes with atoms, molecules, or ions? Just follow the steps. Follow the conversion factors. Atoms, molecules, or ions, that's 6.02 times 10 to the 23rd molecules, atoms, or ions. In this case, it's molecules. What number goes with grams? You need a periodic table. If you look up oxygen, it's 16. But there's 2 of them, so you need 32 grams per mole. Okay, be careful on that. So take 4.31 times 10, that's second function EE, 22, times 32, press equals. Don't forget to press equals. Divide by 6.02 times 10 to the 23rd. You end up with 2.29 is the correct answer. 2.29 grams of O2. Okay? That's it. That's mole calculations. Okay? We will definitely beat this more up in class, but for now we're done. Okay? Email me with questions. Give it a shot. Press the pause button as often as you need to get what you think you need.